Are supply chains and AI supply chains as same as they sound? Let's explore what is AI supply chain. How are they both alike and what sets them apart? When one thinks of upstream, midstream, and downstream supply chain, it is very easy to come up with many examples. But come to think of it for AI, you'll be left scratching your head. Similar to traditional supply chain, AI supply chain also involves various businesses. One curates data, another trains models, and the third fine-tunes them for specific uses. Upstream components include base models like GPT-4, Anthropic's Claude, and Google's Palm 2. These components are versatile and can be repurposed in various ways. Downstream components are user facing products like AI driven hiring tools, writing assistants, or shopping apps. Wedged in between are midstream components that act as intermediaries, such as models that summarize resumes or datasets of AI generated outfits or data labeling tools. Base models like ChatGPT require a lot of computing power and a sound investment. A startup would typically require an investment of over $500 million in order for them to develop their own large language model, a technology that underpins ChatGPT. Hence, it is not possible, and only a few businesses have that kind of capital, like Google, Meta, and Microsoft. Creation of these base models has caused a gold rush into startups such as Mobius, Stability AI, and LangChain, who are essentially leveraging on powerful base models and datasets and are working on softwares to help other companies incorporate AI into their products or businesses. Moving forward, we will continue to see most AI driven products are built on a chain of AI components rather than built independently. Let's dissect how robust AI supply chain is. For that, we will study the recipe of success behind modern day supply chains and later compare how AI supply chain performs to those. What is remarkable about modern day supply chain, such as auto manufacturing, is that they generally work. One reason why most supply chains are manageable is that their individual components are well specified. That is, we know what purpose each component in the supply chain serves and how it is expected to perform both on its own and with other components. For example, the success of auto industry depends on the ability of each company to provide a part on time and to ensure all specifications and quality standards are met. Another factor that contributes to its success is modularity, which essentially means that supply chain can be broken down into distinct components. For example, when the brakes are recalled in the 2006 Subaru Outback, Subaru knows what to provide the local dealer with for the replacement. The number of people impacted were greatly reduced due to quick and explainable responses. What supports modularity here is the presence of redundancy. Redundancies ensure that when one manufacturer or transporter fails, the other takes its place. Fourth reason existing supply chains work is that we can track provenance of each component all throughout supply chain. Tracking the provenance of each component helps explain and fix failures, making the supply chain resilient even during widespread disruptions like those caused in 2021 due to COVID pandemic. Now let's have a look at how AI supply chain stacks up to these variables we've just outlined. AI systems currently lack formal specifications and standardized performance guarantees, leading to a significant gap between developer expectation and actual deployment outcomes. This gap is what's being termed as poor specification. It contributes to challenges in robust performance, explainability, and bias. For instance, suppose that one company develops an AI model to caption photos, and that this company's training data only contains photos captured in people's phones in everyday life. Say, however, that this training data is sourced from another company that never specifies this fact. That is, they never state what type of training data they use or what criteria they use for labeling. This lack of specification can cause other models to incorrectly assume that the first model performs well on all phototypes, propagating unanticipated errors. As AI systems become integral part of larger supply chains, the risk associated with poor specification will increase and amplify as we go downstream. AI systems tend to interact with each other in a non-modular way. The way that components are combined when building such a system, and even the order used to combine them, matters. And disentangling the roles of each component after the fact is difficult. One can think about it almost like cooking soup. Once all the ingredients are combined, it's hard for the recipient, or in this case of AI, the end user, to determine what went into the soup or how it was made. Although tools are being developed to deconstruct these influences, however, there is a long way to go. The problems posed by non-modularity are further amplified in a multi-layered supply chain. A prime example of this is transfer learning, a process in which an AI model that is trained on one task is then adapted or fine-tuned for another. Think of an AI model that is trained to translate between English and French, gets fine-tuned to perform translations between English and Spanish. This fine-tuning changes the adapted model permanently, making it difficult to trace the behavior of the new model back to the behavior of the first model, exacerbating the problem of poor specification. We saw previously that in modern day supply chain, should a manufacturer or a transporter fail, others can compensate. Industry standards, together with regulations, enable this replicability and compliance. However, in AI supply chain, regulations and standards are in their infancy, hence compromising on modularity. Let me explain this through an example. Consider there's a credit union who uses multiple AI models to decide on lending decisions. An upstream model predicts mortgage defaults, while a downstream model uses these predictions to recommend interest rates. If both models are trained on similar datasets, the downstream model would produce biased or overconfident recommendations, or simply put, would fail in providing an accurate recommendation. Note, due to non-existing standards or regulations, it is incredibly challenging to find alternates for a failed AI component from other operators in AI supply chain. Comparing to modern day supply chains, currently AI supply chain observes limitations in provenance. However, this might change in future with the arrival of C2PA and content credentials, which essentially empowers content creators and editors by disclosing information about how an asset was produced, what was changed, and how was it changed. This will enable tracking history of an asset and making applications visible that were used to make changes. To summarize, modern day supply chains have been through the test of times, while AI supply chain are still in their early stages. Benchmarking to supply chain's strength is one avenue through which AI supply chain can incorporate big improvements. This will certainly be a win-win for everyone. With that, we come to the close of our first episode. Stay tuned to our AI series, where we uncover inherent risks, limitations, and the need to regulate AI. We would love to hear about your thoughts in the comment section below. Look after yourself and thank you for watching.